So, welcome to this afternoon session. In the spirit of making change happen, this afternoon we are rethinking the architecture for the edge. Basically looking at a scenario that's kind of impossible running Kubernetes with just 2 nodes. But you'll see. I've brought with me Andrew.
Yeah, I'm one of the field product managers on the Edge BU at SUSE.
And David from our partner Synadia.
Hey folks, I'm going to apologise first. I'm English, right, and that meant I never made it yesterday because our airports are going through some kind of dark ages puberty where things are just going back into the past. So yeah, it took me 20 hours to get here for a 2-hour flight, so that was all my fault. So nothing on these guys' fault, it was all on me, so apologies for that.
Yeah, and thank you for showing up anyway with a rescheduled talk, and I think it seems the topic matters to you. I'm Joachim, or Joe Werner. I'm the Principal Product Manager for Edge at SUSE. Yeah, just quickly the agenda for today. Obviously, we are looking at the motivation, why 2 nodes to start with. Then David will guide us well, through the architecture and also give us a demo. Well, we've recorded the demo to be because we chicken out in terms of live demos. That's how Jay put it yesterday. And then we'll also give you a bit of an idea how you can get engaged with the project, either by contributing or by working with us on a pilot or taking your use cases into consideration. So let's start by looking at the motivation. I want to first go into why would you do Kubernetes at the edge first. I guess most of you, since you are at a SUSE conference, you're either coming from the Rancher or the SUSE side, you're probably familiar with why you would do Kubernetes. What we've learned in the last couple of years is that it's very attractive to take the whole cloud native concept to the edge, because basically that means for your engineers, for your developers, for your IT department, that the edge is really just an extension to your cloud native environment. So it's just another deployment target. And that's what we want to make happen. There are 2 use cases that are really from our daily work. One is a restaurant chain use case. Restaurants usually, fast food chains, so they have this kind of kitchen management system where someone goes, orders at the kiosk or through the web app or at a counter, and then of course someone in the kitchen gets the bill of materials to basically prepare the meals, and then you have to hand it over to the customer. Those systems also usually are integrated with monitoring things like the temperature of the deep fryers and so on, and there's a lot of data collected. And then also increasingly they do some like vision-based workloads, like having a camera track the length of the queue at the drive-through or drive-by, whatever counter. That's one of the use cases. And in a restaurant setting, they want to keep it cost efficient, but still they need HA. And another one would be an industrial automation case. So this is from a company that's building large bottling plants. Think of Coca-Cola or similar, like really large plants that have an output of thousands of bottles per hour, or even sometimes hundreds per minute. Super fast. And they are starting to rethink the architecture. They have relatively large PLCs, so controllers for each of the parts of that big machine that is kind of like a whole building. It's a huge thing. And they're trying to span a Kubernetes cluster across that. So that would be another case where you'd look into Kubernetes. This could potentially be like also a larger cluster, but 2 node is like the bare minimum. If you're looking at the topology, do you want a single node that's super simple but may fail, obviously, because any hardware failure means the complete environment is down. 2 node is kind of the middle ground, or a multi-node. You look at how limited is my budget. Obviously, if budget is not a concern, it's always better to have another fallback. Do I need HA in the first place? Yeah, of course, if I'm fine with temporary outages, or if I have a much larger problem, if let's say power is down, my store is offline anyway, so who cares whether the server is down too, then maybe you don't need it. How much downtime for updates? Because that's the thing, even if everything runs smoothly with a single node, yeah, you have to update it from time to time. So if that's something you need to do regularly and you can't afford the downtime, like you're a 24/7 store or so, then yeah, definitely look into how can we do HA setups. And finally, how variable is my compute workload? To give you a simple example, if you have workloads that are pretty dynamic, so you have spikes, then obviously if you have just one node, the node has to be as big as or as large as your largest workload that can happen. On a 2-node cluster, if you are planning for being HA, so you can lose a full node, yeah, here down to a single node. So you have to basically plan for all your critical workloads to run on just that one node. A 2-node active-active setup gives you a bit more headroom, of course, for dynamic workloads that you can schedule when there's free capacity. So I'll hand over now to Andrew to talk about when the 2-node is the right choice.
Thank you. Yeah, so part of this project kind of came out of a lot of customer conversations where we were being asked to be able to support a 2-node. And most of those conversations really fit into places where you couldn't get enough power, you were constrained on a power budget, you were constrained on a cooling budget. For example, if you're in say you've got a couple pieces of hardware that are in an industrial setting, and you only have so much cooling that you can actually pump into that because you've got, say, I'm going to say a square foot, but that probably doesn't work in the
Call it a small box.
Yeah, small box. So you've got, you're limited on physical space. Like Joe mentioned, you're limited on cost. And that you have symmetric workloads so that the workloads actually know that they're running on 2 nodes, and they're not having to worry about any of the storage or as much worrying as much about the storage of the 2 nodes. So that's kind of where it makes sense. Where does it not make sense? Most everywhere else. So obviously in the data center, just buy 3 nodes, right? Or by however many nodes you're actually going to need to be able to run your workload. In the cloud, again, just if you need 3 nodes, spin up maybe 3 smaller nodes, right? And be able to balance your budget that way. If you have the budget, be that power budget, actual budget, cooling budget, 3 nodes is going to be a significantly better way to go. When your data quorum is very important, again, because the workloads would also be running in a 2-node HA configuration. So you need to make sure that not only is the underlying platform HA, but the workload and the storage is also HA. If data loss is a problem, then 3 nodes is going to be what you really want. And then lastly, when you might have an unsymmetric workload, or another place that it would not make sense is if you have, say, physical hardware being plugged into these nodes, where the compute resources need to be tied very specifically to physical hardware. So basically, anytime you have any money, space, power, cooling, really anything that you're able to run 3 nodes, it's better to do that. But that said, we've run into enough places where 2 nodes is the right choice, so we built it.
Let me get to the fun parts. Actually, I'm just going to go back here because these are kind of interesting. It's kind of like we're telling, well, actually, don't do 2 nodes. You just kind of want to do 3. But what we're kind of saying is the problem changes. So as you go to smaller machines and more of them, instead of having, and I described this earlier really badly, I think I kind of said instead of having 3 machines at $10,000 each, you might have 1,000 machines at, $300 each or something. The kind of dimensions of the problem change. But obviously, if you're going to talk about fried chicken and you miss a few temperature readings, but you can interpolate between the misreadings, if there are any misreadings, it's like the value of the data is different the further you go out and the closer you get out. Like, and even on a factory floor where we're now talking about real-time movement and precision on some of those machines, it's not necessarily that the workloads are going to lose anything. It's just that what if something happens? So even in the two-node system, if something happens and one of the nodes goes out, and I'll go into this when we get into the architecture, there might be something missed. But because those use cases are different to, say, a banking system and a transactional system, is it really such a massive problem? You know, is one gonna really hurt if you can replay a misvalue at the point of failover? So what we're really saying is here, the paradigm changes when we start talking about a two-node system versus a big, bulky three-node system. That's not to obviously jump on anything that we're saying. It's just an interesting conversational piece that we can, you know, certainly talk about till the cows come home, to use a British expression. So architecture and overview. So like all good things, we've taken NATS, so the open source NATS project, and we put it into Kine. So there is a Kine patch now where you can take NATS, you can replace etcd, and then run a multi-node K3S cluster without etcd. That didn't really solve the kind of problem, obviously, the two-node issue. So what we've done is we wrote a two-node leadership election engine that is very, very deterministic. So we minimize the number of inputs it has, and we minimize the amount of decision-making capabilities it has. So when you see FSM, finite state machine has some inputs, so it knows about the network. Local API, which is a state of K3S at the moment, it can run local operating system scripts, so it can do things like arbitrary checks to make sure a GPU is present or the storage is less than 8% utilized or something like that. And it does neighbor check, so each of the nodes check each other, A, for reachability, and B, for availability of meta information that needs to make those decisions. So that's the kind of stuff going on the right-hand side. I'm trying to think, is this a laser pen? Oh, it is a laser pen, how about that? Yeah, so on the right-hand side, over here, so the finite state machine is a massive set of if-then-else statements. I mean, it's huge. We've got a number of probes, and the probes are autonomously and they're massively concurrent. And obviously, any time that you're working with sensors or information, you have to debounce the information, right? If you have lots of oscillations and lots of noise, the system can make a terrible amount of decisions, and they'll all be wrong for that moment in time. So we debounce and wait before decisions are made. And then when the decision is made, a number of meta keys or metadata keys are set. So we now know what node at that point should be a leader, what should be a follower. We also then know if it's been configured to set a floating IP address, so you don't need any other system here to be able to do, say, an active-active failover. So with a floating IP, for instance, on a leader, obviously if that one fails, it moves over to the follower. Floating IP moves with it, which means you can have one DNS entry for your workload. You don't have to go off and change any of those things, and it's relatively straightforward. So it's one component for the leadership election engine with Kine, with K3S embedded. So two binaries, some configuration, deploy, system reconciles some basic state, and then it stabilizes with no decisions. Now, we've had all sorts of interesting questions, even in just this kind of last day. So like, what happens and if, then, and else? And I'm going to go through some of them in a moment. But on the left-hand side, then it's like how it manifests in reality, right? So this outer box would be the machine with K3S, with the TNE or the two-node engine, the FSM and NATS all embedded in a single binary, and then we drop those things out. Now, the reason the layer 2 switching is there is because the floating IP uses netlink with Linux. So we implement an IP address, and then we do gratuitous ARP requests and basically announce to the network that this IP address lives here. And we do that to the point that when the GARPs stop, I say from a leader, and then a follower that takes over into the leadership position will carry on doing those GARPs to basically force the IP address across. Now that's important because if you are on an overlay, a network overlay, and you've got broadcast turned off, the floating IP is not going to work. I think I just shot you with the laser pen. Sorry, mate. It's like, phew. Yeah, that's not going to work. So you need to be mindful of allowing those broadcasts. Now, but we've got a workaround for this coming up. And also this means if you're thinking, hey, this is interesting maybe for 2 data center and which one should be active, we've also got a pattern for that coming out as well. So if I just go through the basic states, and I'm going to do this by power of dance, right? We have 2 nodes. We have something called a configured leader and something called a configured follower. So these are biased at boot time. Configured leader comes up, configured follower comes up. If all conditions are happy and correct, we have stability. We have the leadership, we have a follower, the VIP is on this side, and then we have 2 nodes in a resource pool. So then you could say, hey, throw these pods, and we want 2 pods on each, whatever, in the system. So you have this kind of notion of symmetric workload. But then, to Joe's point, then you could say, well, actually, providing that there's enough resources left, I want this whatever. I want a connector to kick in every now and again, or a cron job or something, so you can run dynamic workloads. And if a node disappears, obviously the scheduling will kind of be priority-based, take away the things that can't be run. But let's say, right, we have a network problem, and some of you are going, oh, what about split brain, Dave? And what about cap theorem? We know we've been talking about this for the last year and a half, give or take. So let's say we have a split brain, and the configured leader disappears. Okay, so now we have a configured follower in follower mode. A number of timeouts happen. I'm a network guy, so the number of timeouts is 3. Of course, it's always going to be 3. And then a number of state changes happen. They go into the finite state machine. This thing says, I'm now the leader. I am convinced I'm the leader. Now, the guy that's been cut off could be saying, I'm alive, but I've got no visibility. And it knows enough to impair itself. And I got told off in a coffee shop, actually, in the UK for this. I was describing this to my dad. And I said, the way it works, it kind of shoots itself in the face. And he went, oh, yeah. And this lady came up and she went, young man, I've got a problem with you. That's terrible language and you should be ashamed of yourself. And she told me off in public for saying that. So I said I wasn't going to say it in public again. Anyway, so it kind of shoots itself in the face and shoots itself in the head and kills itself. But what it does, it basically puts itself into a holding position of impaired until the conditions change, and to which point it can come back up. So we're in split brain. This thing has took over. Now, what happens is the write flag changes with it. So we have a read-write data store still. So split brain, we have a transition. Now let's say this other node comes back online. What's going to happen here? So we've designed it in such a way where when the leadership moves across, it latches in place. So even if this node comes back, it says, oh, my neighbor's up, so I'm now going to be a follower. And it just waits. And you can manually put it back. But the question is, why would you want to do that? If you've got 2 nodes running a piece of machinery, and let's say the longer the machinery is alive, the more data it generates, there's going to be a little bit of reconciliation time for the data stores to catch up. You don't want the blip. Just leave it alone. What's the point? Unplug it, plug it back in at night time, maybe when the cleaner comes along and kicks a wire out to clean the floor. I don't know. But you don't want to be really doing that. So it latches across. And then let's say you do want it to go across to do maintenance, and you can manually move the flag across and the states change. And then the data buckets underneath will swap over. And it's only at the point when they're both correct and the sequence numbers are correct in the data stream that the read-write flag basically is re-implemented to accept the changes. So we've got a number of conditions there to help with instability, with maintenance, being able to swap things in and swap things out. And then one of you, I'm sure one of you is going to be thinking this. Certainly Andrew is, right? What if a node blows up and the configuration dies? Not a problem. Providing you've got one node up, bring a new node up with basic configuration, bring it online, it will resync automatically. And then it will tell you, and I'm going to show you the demo in a minute. I promise this is not just me talking at you for the next 30 minutes. It will basically say, hey, I'm synchronized. I've got a good set of states. So interestingly, this is going to be a fun one. How many of you are familiar with K3S? This is kind of important. Okay. Yeah, that's a good info number. So some of these things are going to be important. Are you familiar with the health check system? So there's a HTTP endpoint. So at its most fundamental, you can do a check, you can do a get. If it's 200, everything's fine. What's the number that comes back if it's not fine? Anybody? 500. Who said that? Right, you can have a sticker. I know you're going to feel really proud of yourself at that point. We're there waiting for you. 500. You get a 500 back, but there's a little known thing. You can put verbose in as part of the path, and then you get a little screen printout of everything that's working, everything that's not working. So the state machine now has an FSM Z. I nearly said Z because I've been working for American companies for a long time. FSM Z endpoint, and it's very much in the same guise as K3S, where we expose metadata with a 200 and a 500 star rule set, so you can monitor and observe these things. So thankfully, I'm not on this video, but I'm just going to walk back so I can talk about it properly. I know I can see it on the screen. It's kind of pointless. On the left-hand side then, the top left, is the FSM Z endpoint from the leader, the configured leader. Top right-hand side is the follower. And you'll notice some keys, which I've just put the black screen in front of. We have, this is a memory task now. I'm just going to wait because this is kind of embarrassing. I'm not going to get this wrong. You can see what we're doing here, though. We're deploying, we deployed Helm with HA proxy. And then we'll deploy Nginx just as a workload in a moment. The reason it's Nginx is I'm using it as a really, really cheap web server, nothing else. I'm not using it for load balancing. It's just I can cheat, and it just drops up the default payload. That's what's going to happen. And in fact, when I go back to the other screen, I'll just pause this. But I wanted to show you the metadata that it comes out with. and how easy it is to see what the system's doing. Watching here to see Nginx come up, and then the next step will be to show you the VIP working and the payload actually running in the workload. I kind of forgot I'd be in front of a crowd at this point. There we go. Right, so I'm just going to pause that. So on the top left-hand side then, we have local API. That check basically is an internal check. It checks for the K3S API to make sure everything is happy and the system is online. We've got local OS, so that's operating system check. That's an arbitrary script you can configure. It doesn't have to be anything, you can leave it alone, but it might be the presence of a specific hardware module. It might be enough storage, enough memory, something to run your workloads, right? Your workloads at this point are going to be deterministic. You're not in an elastic compute environment. It's not a case of just add more servers and throw more money at the problem. This is a very constrained problem. So your OS check can check the environment for meaningful things. Probe network liveliness is two things. It's ICMP checks, and it's a HTTP check to its neighbor's FSMZ endpoint to basically get all that metadata and treat it really as key value pair data. Floating IP, you see this on the true? So on this side, we'll have the floating IP configured. True basically says, I'm alive, I'm a leader, therefore I've got the IP. The IP is configured. The GARPs are going out to the network. And then on the right-hand side, you'll see floating IP false, and obviously the GARPs won't be running. And the configured leader state is leader. The states, as per one of the previous slides, can be leader, follower, impaired, and leader RX. And leader RX is a bit of an Easter egg, but it basically means it's the leader on the follower side when it's stood up through this kind of logic decision matrix. And then FSM posture. So this is kind of giving you hints at what it can be, right? So when I was building and debugging this thing, you can imagine the sheer amount of things that can happen simultaneously. I was trying to wrap my head around all the various states. So I basically gave myself some clues. So I'm the leader, I can be follower if my role is reversed, and it'll do all sorts of things as well if you're in impaired mode, and I can come back up if the OS check passes and things. It'll actually tell you to a degree what's wrong. Ready as follower false, well I'm the leader, so I'm not going to be a follower. And then transitioning, this is this mechanism of the latch. So with these two systems, leader follower, if the leader dies and the follower steps into leadership, it latches into place. Now there is a preemption mode, but with that you accept that once the network's happy and the conditions are happy, it will automatically fail back. Thus, you're going to get an interruption to, say, VIP moving across the network. So the logical thing is, if the problem space is constrained, the workloads are constrained, then why does it matter which one's a leader and which one's a follower, right? Because it's still one resource pool. And symmetric workloads are important for the VIP. Obviously, the VIP can't do magic. It's not going to know that there's one resource running on, one machine versus the other. And then you get the calculated state with the leader and follower. So I'm just going to let this thing play through to completion. That's not happened. This is down to embedding a YouTube video. All the best things. Right. I need to get it back to a point where actually it showed you the workload coming up there, I think it was. Right, so then we see the site can't be reached, so we're trying the workload on the VIP, and within a few seconds, oh, come on me. This is not embarrassing. Right, apparently I'm going to disconnect the NIC next. This is disconnecting the NIC on the follower. So on the leader even, on the server one. So you can see the workload's running. This is a VIP now pushing traffic at node 1. Now I disconnect, and you see that? We've got the circle of doom, the spinner of doom. The FSMZ is disconnected because I've literally pulled the cable out the node. And then what happens? A neighbor transitions within a few seconds, and the workload carries on working. A few moving parts kind of make this happen. Again, this is 2-node, real-life K3S with this leadership election mechanism. And that's really kind of it for what I wanted to show you, but everything else works at this point, right? So we can plug the other node in, it will come back up, it would reconcile, we can move things around, we can kill a node completely, bring a brand new node up. I just wanted to go through and not kill you by talking at you and showing you endless amounts of videos. So what I would like to do, any questions that you've got, keep them in your head, write them down. We want to get to the end, because I know some of these questions can be like a black hole. They're going to be time consuming. And any really big questions, we can just wait outside as well. So thank you, and I'm going to hand back over
Awesome.
and pass the clicker. Cheers.
Yeah, so you can see that we've got this up and running. So what's up next? So the first part is we're looking to work on some stateless config. So basically setting up and doing an actual leader election without having to pre-bias the system. That way we don't have to install one system as the leader and one as the follower to start with. Then that obviously makes everything easier, both from actually writing the system as well as the operational workload for the people who have to do the setup. Probably going to be based on CSMA on the networking side, or potentially based on Mac. We're also looking at embedding a BGP daemon so that we can be routing on the VIP as opposed to having to send ARP announcements all the time. And then lastly is IPv6. Currently, it is IPv4 only. And actually, I'm going to ask, would that be dual stack or? Okay, cool. So dual stack as well, right? Well, yeah.
Yeah, sorry. So V6 and V4. Should have made that really, really clear. So it's not V6 or V4. No, it could be dual stack. Yeah, and the same for the BGP.
But like right now, like so many components are. So it's really annoying. So and that should be pretty easy to do. So if you want to get involved, this is all merged into Kine, and so you can run K3S with this setup in full cluster mode. That's not the 2 nodes, that's the Kine with NATs, so that way you can actually start seeing how NATs works. And I'm going to just throw out there that there's a lot of value to using NATs as the data store, even outside of the 2 node piece. There's for example, it allows you to we were talking through a lot of the ideas of like the value that you could get from this, but like for example, you could actually spin up a system and have it look as if it was a system that was just rebooting, right? Because you can already have all of the historical events basically preloaded, right, and memoized at that point. So definitely check that out. Test it, play with it, contribute to it. PRs are always appreciated. So the 2-node engine is currently proprietary code. We were having conversations about the best way to get that to be open source code. There are reasons that it's not open source at the moment. But if you want to play around with the 2-node, please contact either SUSE or Synadia, and we can get the code into your hands, and allow you to test it, play with it. Have fun with it. Thank you. Questions? Is there a question? Yeah. Any questions?
Nobody has a question.
I do not believe that there's no questions. Okay. Actually, I'll just repeat it, Joe. So he was, or do you want to? You can go.
So you have 2 nodes, and the second one, which is the follower, doesn't host any workloads. It's just a hot spare where all the stuff is migrating, where the node 1 master is down.
So it actually can be active-active. So you would not want to have more workload than one can handle, but you could run workload that is preemptible on that spare. So that way you can actually pool the resources, and then when you're in a failure mode, shut all the non-essential workload off and then fail over to it. So you get more resources than just one node, but it's not dependably so.
And to just add to that, at the point of deployment, the demos that we do, the same workloads go to both nodes. So when the VIP moves across, the system is ready to go. And the underlying data stores for K3S itself are ready. Now, that's obviously going to pose a lot of questions, right? What happens to the data for the application itself? Which is why the problem space is constrained. So if we talk about chicken fryers, it's probably fine. If we talk about bottling plants, probably fine. But if you say, well, that's not going to be good enough for a bank, Dave, well, I've got to argue if you're going to put 2 nodes into a bank, you might have a few problems. It's probably not the best approach.
I question your decision matrix.
Okay, thanks. And probably the second one, because you already mentioned, why do you need the custom code for that when CoreSync, Pacemaker, and Virtual IP could do literally the same? Never tried, but in theory.
Right. Okay. So again, I love this. I kind of knew this would come up. It was almost like we could have had a top 10. Why do this and why we broke it out? So number one, all of the components are in one binary, one deployer, one deployment. So NATS, Kine, K3S, two-node engine, the VIP management is in one system, one service. You just deploy it, done. And it's all controlled from the NATS KV bucket as well. And signaled.
Thanks. Sold.
And the nice thing is, because of that, we can add things like the BGP daemon as well and advertise /32s out from the network, all in one simple deployment. I mean, all the demos we do today are all systemd based. So we just kind of throw it on a crappy machine, do some tests, do some demos, throw it in the garbage and start again. Configuration as simple as just run it with a config file and you're away. And the lovely thing, I think we kind of just alluded to this. I think we've got time. We can do this. We can go back. When we go to this, like, what about NATS? So you can run this. In fact, that's not the one I wanted to be on. It is. Sorry, no, I don't know what it is. I'm lost. I've lost myself here. Yeah, this one. Yeah, so run K3S with NATS in full cluster mode. It's not just about swapping out etcd. It's not like, well, why swap one thing for another if the outcome is the same? With NATS, you've on the same system, you've got key value object store, data streaming. So you could replace Kafka-style workflows, KV-style workflows, MinIO, Redis, etcd, all on one system. So one component that's clusterable geographically in one end, global cluster, all on one system, all on net. So actually what you get is you kind of like get compound returns by swapping out a load of stuff for one thing, and it just so happens you can run two-node, multi-node, K3S on top, just to help. I know we can talk about this all day long, but I think some of these things, they get lost in the communication sometimes.
Yeah, I sort of have the image in my head, and if you would like type kubectl get nodes in the cluster, then each cluster would only see their themselves, right? Because you did the HA part, you sort of have this in your TNE binary, and you don't need really the cluster mechanics of Kubernetes, right?
Right. Yeah. So this is really interesting. I love these questions. Damn, I wish we could just do this all afternoon, to be honest. I'm not saying that's great for any else of you, but so if we go to this, what we actually have is the two nodes, despite being in separate boxes, they're combined to be a pool. So they are a pool of resources. So if you, and this is where obviously having the hardware here would be good. There is a live demo, by the way, on the exhibition floor if you want to go and play. You can do it and run the commands yourself and see. But if you did like the get nodes, you'd see both nodes there in a resource pool. They're not separate. They're the one thing. What confuses a matter is there's a VIP, making you believe they're two disparate systems. The VIP is there for symmetric workloads. So you could have two different workloads on the machines, and you could go to the nodes separately, and they'd serve them. But the VIP is there if you had, say, 2 Apache web servers or whatever, and you didn't want to use anything else. The VIP is there as a convenience, not as a signal as to how the system architecture looks. So that probably wasn't overly clear, but hopefully that's clarified that.
I guess it's also, tying into your question, your earlier question, it's basically not 2 Kubernetes clusters running in traditional HA mode. It's one 2-node cluster that happens to, of course, be set up in a way that if you have an application that itself has to be HA, make sure that you have the virtual IP and run 2 instances and so on. So,
and it's solving
in terms of
a different.
Yeah.
I was about to say it's solving a different split brain problem of when you have one layer, like one scheduler sitting above another scheduler. They might get out of sync, right? So this solution allows us to make sure that they stay in sync, and that you don't have weird. This is coming from when we were running Cloud Foundry on top of Kubernetes, which was always fun. But you would have issues where the two didn't agree with each other, and the system would start failing, right? For very weird and hard to debug issues. This solution sidesteps all of those potential problems because the entire stack knows about each other.
Yeah, and obviously as long as you have both nodes up, you can basically schedule non-HA workloads, and Kubernetes will make sure it runs on the node that has capacity. Of course, with a caveat that the stuff that has to be always on, that's where you run 2 copies, make sure that they are running in a 2-node setup and with a VLP setup and so on.
Was that it for questions? Really? Oh, was that a hairbrush or a... there we go.
Yeah, I tried K3S before, and then I saw that it doesn't boot up properly if there is no network connectivity. Then the pods don't get an IP.
That's correct.
How do you solve that if, for example, in the edge, the full stack loses power and then boots up, and then the nodes happen to boot up quicker than the network stack, for example, the HTTP server? How would you solve that?
So are you asking like if the switch is not online yet?
Right.
Okay. I would honestly in systemd I would probably put a unit file that says that K3S wants, and that waits for the network to be online.
To wait for the network.
Yeah. The way we're solving it for systems that don't have any network at all, and so this wouldn't be for the 2-node, but like if you didn't have any network and it was just a box, we're just using a dummy network. So we just tell it there's an Ethernet port there, even though there isn't, and that will sidestep. But yeah, it does need an IP address allocated to it, or you could use static IP addresses as well.
Okay.
Yeah.
Thank you.
Just to add to that, is this an ordering problem, or is this a system-level design thing where you're running maybe in an isolated system? I'm kind of curious. So is this like going through the loop back from the system to itself, or is this like an isolated system at boot? I'm kind of curious as to the question.
Well, a kind of a cluster that runs on a system, or it can be a 1-node cluster or a 2-node cluster. And maybe you can connect it to the network or not. Or someone can disconnect the cable who doesn't know what the cable is about. That kind of situation. In the edge, you have a difficult situation that people that manage the system don't know what they are doing.
Yeah, people are people. That one's tricky.
I would say that at least my understanding is that would be a Kubernetes issue, not specifically a K3S issue, and so it would be something that either we would have to design around for the holistic solution, like add in some power management to say the switch has to come alive first before the nodes actually get booted, or I think you could probably solve it one step back or a step further up the stream. What is probably the better way, but yeah.
Okay, thank you.
Thank you.
And I think, in the 2-node cluster setup, obviously, if just one cluster doesn't have network anymore, then your checks jump in and will try to definitely degrade it and at some point try to bring it up again. Yeah, we show that down there.
Yep.
Basically just unplugging or switching off one of the devices. And
and actually this is, just to be really truthful, sometimes K3S and Kine will absolutely try its hardest to crash the system, and it will throw everything at you to try and just kill itself. And what we're having to do is basically go back through the code to stop it from doing that. So with the NATS integration, it's like we need the thing to be online, stop trying to kill yourself. So we're trying to go back and patch it to make sure that when you run 2-node, that this whole vicious cycle of it going, come on, die, damn it, we've got to stop that. And that's still causing problems. So if you rip the network cable out, the TNE system stays online. It says, oh, I'm impaired. And all of a sudden, it's like Kine says, I'm going to die. And then obviously, because everything's embedded in one binary, the signaling from K3S and Kine kills everything. So we have to rapidly reboot the thing. But we're working on that to get a PR out to stop that happening in the NATS version, because we need it to stay online because of that problem. So yeah, truth be known, it's a real nightmare, but we're getting there with it.
Yeah, the joys of cloud native, where it's, if I'm at all impaired, just die and restart, becomes a problem.
I'm not going to force questions out of you. If there's no more, thank you very much for coming along. And yeah, cheers.
Yeah.